All right, welcome to this explainer. Picture this. You're standing right in front of a whiteboard, marker in hand. The interviewer looks at you and drops the ultimate prompt, design Dropbox. Or, Google Drive. It's an absolute classic, one of the most famous, massively scalable system design questions out there. But today, we're not just going to sketch out some basic file app. We're tackling this like a staff-level engineer. I'm going to be your mentor today, and we're going to dig into the exact trade-offs, the hidden bottlenecks, and the sheer massive scale that separates the okay candidates from the hired ones. So grab a coffee because cracking a system at this scale, it takes some serious rigor. Here's our roadmap for today's session. First, we'll look at the interview roadmap itself. Second, the baseline architecture. Third, we'll do a deep dive into scaling uploads. Fourth, validating those uploads. And finally, perfecting the sync strategy. Okay, part 1, the interview roadmap, or the path to staff level. This right here is the core methodology every senior candidate absolutely needs to use when they walk up to that whiteboard. Without a roadmap, honestly, you're just drawing boxes and arrows blindly. Think of this as your compass. Step 1 is requirements, figuring out what the system actually needs to do. Step 2 is core entities, your files, your metadata. Step 3, APIs. Step 4 is the high-level design, where we actually start drawing the architecture. But here's the real secret. Mid-level engineers, they usually stop at step 4. They draw it basically works, they dust their hands off, and they're done. Staff engineers, though, this is where they shine. Step 5, the deep dives. This is where we look at our own beautifully drawn design, completely break it, and then fix it so it can actually handle massive real-world scale.
Moving on to section 2, the baseline architecture. Just simple boxes and arrows.
To build our foundation for step 4, we've got to draw out the initial flow. The basics are super straightforward, right? Users need to upload files, download files, and sync them across their devices. But to do this right, we have to lay down a really critical non-functional requirement from the get-go. Thinking about the CAP theorem, we are actively going to prioritize availability over consistency. So what does that mean in plain English? It means if somebody updates a file in Germany and a user in America tries to open it literally a split second later and sees the older version, we're totally fine with that. That is an acceptable trade-off. We'll take eventual consistency every time if it means the system is always highly available and doesn't crash when users try to upload or download. But right when we're feeling all cozy with our basic flow, we have to slam on the brakes for a massive dose of reality. 50 gigabytes. That is the actual, literal maximum file size that Dropbox supports today. And that brings us to a total roadblock. Think about it. If we stick to our baseline architecture, where a file goes from the client through our API gateway, into our file service, and finally into blob storage, we are walking directly into a trap. Standard managed API gateways, like the ones you'd spin up on AWS, usually have a strict request payload limit. We're talking like 10 megabytes. So a 50 gigabyte file, it doesn't just slow down our baseline architecture, it completely breaks it. We wouldn't even make it past the front door. So let's jump into section 3, deep dive on scaling uploads and bypassing this bottleneck. This is exactly why we pivot into step 5, those staff-level deep dives. We have to completely bypass this bottleneck. And our first real staff-level superpower here is using pre-signed URLs. See, instead of forcing a massive 50 gigabyte payload through our own API gateway and file servers, which, let's be honest, is a huge waste of internal bandwidth and CPU, we change the flow. The client sends a tiny, lightweight request to our file service with just the file's metadata. Our service says, okay, you're authenticated, and request a pre-signed URL directly from blob storage, like Amazon S3. We hand this secure temporary link right back to the client. Now, the client uses that link to upload the heavy 50 gigabyte file straight to S3. Boom, we've bypassed our entire gateway entirely, saving our servers from doing all that heavy lifting.
But hey, we still have a physics problem, don't we? Uploading 50 gigs on your average home internet can take over an hour. Just imagine being 59 minutes into an upload, your Wi-Fi blinks out, and the system makes you start all over from zero. You'd be furious, right? The user experience would be absolute garbage. The fix for this is chunking. We take that massive file and slice it up on the client side into smaller, totally manageable pieces, let's say 5 megabytes each. Now we can upload these chunks in parallel, maxing out the user's bandwidth. And even better, if the network drops, we only lose the progress of one single 5 megabyte chunk. The whole upload becomes perfectly resumable.
Now, here's the next puzzle. If we're slicing a file into literally thousands of little chunks, how on earth do we keep track of them all? How do we know which ones made it to the cloud and which ones need to be retried? We solve this with fingerprinting. On the client side, we run a cryptographic hash function over the raw bytes of every single chunk. This spits out a perfectly unique ID, or fingerprint, for that specific piece of data. This is a game changer because it brilliantly solves the tracking problem without having to rely on messy, error-prone database indexes. We just look at the fingerprints the client has and compare them to the fingerprints our server has already marked as successfully uploaded. Simple, elegant, and it just works. All right, Section 4, validating uploads, looking at trade-offs, and answering the question, how do we know it actually worked?
Okay, so our client is happily uploading chunks straight to S3 using those pre-signed URLs. Awesome, but this brings up our next architectural dilemma. How does our file metadata base actually know a chunk made it safely into blob storage? Let's talk trade-offs. The naive junior approach is just letting the client tell our server, hey, I uploaded the chunk. But guys, relying strictly on the client is a massive security risk. A malicious client could just lie to us and totally corrupt our metadata. No way. Instead, we have two really solid senior-level approaches. First up is trust but verify. The client tells our server it's done, but before we actually update the database, our server makes a quick API call to S3 just to double-check the file's really sitting there. The second approach, S3 notifications. This is a fully event-driven model. We literally ignore the client entirely. Instead, S3 automatically fires off a notification to our server the exact second a chunk lands securely. Both of these are fantastic options, and honestly, discussing this exact trade-off at the whiteboard is what shows real system design maturity.
Moving to Section 5, perfecting the sync strategy and keeping local and remote aligned.
So, we've nailed the upload scaling. Let's tackle our final challenge. How do we make sure a file change made by a user over in Germany syncs down to a local desktop in America as fast and efficiently as possible? A lot of candidates immediately jump to WebSockets, keeping connections open to push updates instantly. But think about a file system. Updates might be pretty sparse. Maintaining millions of idle WebSocket connections is massive overkill. Instead, the staff-level move is adaptive polling. The desktop client just periodically asks the server, hey, anything changed? If the user is actively clicking around and working, it polls more often. If they're asleep, it backs way off. And when a change is detected, we pair this with Delta Sync. Remember our chunks? If someone tweaks a single paragraph in a massive 50-gigabyte video project file, we absolutely do not re-download the whole 50 gigs. We just fetch these specific 5-megabyte chunks that actually changed. It is phenomenally efficient. When you're actually building out this sync, you're going to face a classic staff-level dilemma on the back end. How do you track these changes? Do you just run a simple query on your database for recently updated files? Or do you bring in an event bus, something heavy like Kafka, and use a cursor to track every single minute change event? Here's the key insight. An event bus is incredibly powerful, no doubt. It gives you a flawless audit trail and lets you do really complex version rollbacks. But it also introduces an immense amount of operational complexity. Unless strict version control is a hard, non-negotiable requirement for your MVP, fighting for the simpler database polling approach actually proves you know when to avoid over-engineering. Championing simplicity is a true hallmark of a mature engineer. And that brings us to the ultimate, inescapable reality of large-scale distributed systems. Despite your adaptive polling, your brilliant Delta syncs, and your robust databases, eventually, something is going to break. A network partition will happen, a client is going to crash mid-write, and suddenly your local desktop state is completely out of sync with the remote server. So I'm going to leave you with this final provocative thought. What is your reconciliation strategy? Because to truly dominate a system design interview, you have to anticipate failure. How are you going to design a background process that quietly sweeps through, compares those file fingerprints we talked about, and seamlessly knits your broken state back together? Pondering that exact question, that is what takes you from a great designer to a truly exceptional one. Thanks for joining me on this explainer, and keep building.